Hi everyone, welcome to Murata Software. Femtet, the CAE software that helps the leading engineers to make their great ideas to reality. I'm Katsuhiko Kosenda. I'm pleased to present you what Femtet is and what you can do with Femtet. Today's agenda. At the end of the presentation, I would like to welcome your questions online. The first, general introduction. What Femtet can do. Femtet is a package of 8 solvers: electromagnetic wave, magnetic field, electric field, mechanical stress, heat, fluid, piezoelectricity, and sound. And Femtet has pre- and post-processors as well. Femtet is capable of multiphysics. It solves the interactions between magnetic field and mechanical stress, the electric field and mechanical stress, as well as heat. And the interactions between heat and mechanical stress and magnetic field are solved. Also, electromagnetic wave and heat, and piezoelectricity and sound. And the interactions between fluid and heat are solved as well. And the mechanical stress solver works with all the other solvers. One of the distinctive features of Femtet is its comprehensive functionalities. Femtet is capable of making analysis model, meshing and calculation, and the results display. These functionalities are available in one package. And another distinctive feature is its streamlined operations. The setups and the user interface are common to all 8 solvers. Now, the benefits from this streamlined operations are: you'll spend less time for simulation setups, and you can spend more time for solving engineering challenges. Femtet can import and export the CAD data. It supports various kinds of formats. Now let's move on to the details of each solver. Femtet solves electrical phenomena with 3 solvers: electromagnetic waves, magnetic field, and electric field. First of all, electromagnetic solver. It solves the electric and magnetic fields simultaneously in the region of high frequencies up to microwave and millimeter wave frequencies. In the communications industry, the 5G technology is being deployed in many countries. Accordingly, the needs for the design and evaluation of antenna and shielding materials are increasing. Next is the magnetic solver. It solves the magnetic fields generated by running current or magnet. You can perform the transient analysis of magnet, coil, transformer, and motor. The third one is the electric solver. You can analyze the electric field generated by the voltage. You can apply it to the designing of touch screen, analysis of the stray capacitance that will cause the noise in the electronic equipment, and the coupling capacitance in the circuit. Electromagnetic solver has three types of analysis: harmonic analysis, resonant analysis, and waveguide analysis. Harmonic analysis deals with the S parameters of the circuit on the substrate, transmission characteristics of the differential lines, antennas' radiation characteristics such as directivity and efficiency. Resonant analysis is used to get the resonant frequency of the microwave resonator, electromagnetic field distribution, and Q value at the time of resonance. The waveguide analysis solves the electromagnetic field propagating in the coaxial lines. Magnetic solver also has three types of analysis: static analysis, harmonic analysis, and transient analysis. In the static analysis, you can analyze the electromagnetic force of the nonlinear magnet, which has BH curve. You can solve the inductance when the direct current is applied. In the harmonic analysis, you can solve the skin effect by applying the alternating current. When you calculate the inductance and coupling coefficient of the coil and transformer, you can take the induced current into account. You can also analyze the electromotive force induced by the external magnetic field. This can be applied to analyze the near-field communications, or NFC, the technology used for the electronic money. In the transient analysis, you can analyze the dynamic magnetic field that changes over time. This applies to the motor analysis, where the magnetic field changes according to the rotation of the motor. You can obtain the torque and the induced voltage over time. Now, the electric solver. There are two types of analysis: static analysis and harmonic analysis. In the static analysis, you can analyze the electric field distribution when a voltage is applied to a dielectric or conductor. Also, you can analyze the capacitance between electrodes, resistance value of conductor, and electrostatic force on the dielectric. You can analyze corona discharge, not a disease. As a notable function of Femtet, I would like to bring to your attention that you can perform analysis of the plating thickness. By calculating the current density, you can estimate the film thickness with the applied time of current. Harmonic analysis. You can simulate the dielectric and conductor. As I mentioned previously, Femtet is capable of multiphysics. All of three electrical solvers can be coupled with thermal solver. When coupling the electromagnetic wave and thermal analysis, you can simulate the workings of the microwave oven, for example. The high frequency is applied to the object in the oven. The electrical energy of the heated object is lost. Its loss is calculated as a heat source and used in the thermal analysis. In the magnetic thermal coupling, the joule loss due to the induced current on the secondary coil is analyzed as a heat source in the thermal analysis. In the electric thermal analysis, the loss of the applied voltage is analyzed as a heat source in the thermal analysis. In this way, you can take the heat into account in your simulation. It allows you to foresee the thermal problems in your product design and take countermeasure in your early stage of design. Now, I would like to introduce the integrated analysis of Femtet and MATLAB Simulink for motor analysis. You can integrate Femtet motor analysis and MATLAB Simulink motor drive analysis. Femtet analyzes the basic characteristics of motor under various conditions and export the results in a MATLAB formatted script file. MATLAB Simulink imports the file and performs the analysis with motor control taken into account. With the motor characteristics obtained by the finite element method of Femtet, you can perform a detailed motor drive analysis. The setup is quite easy. On the Analysis Setup window, you'll find the MATLAB Simulink tab. Select the option to output the motor characteristics file. With some more settings, the analysis model of MATLAB is automatically created. After performing analysis with Femtet, activate MATLAB Simulink. Read the model file on the MATLAB window. Configure the circuit on the Simulink window. Place the module, and then import the motor model. Now we are looking at the results. The open circuit voltage simulation is plotted. Unlike the simplified PMSM model, the nonlinear counter-electromotive force profile is calculated. Like this, analysis with the finite element method of Femtet and MATLAB Simulink allows you to apply the first dimension analysis that is often used for the model-based design. Now, I'd like to give you the details of mechanical stress and thermal conduction. First, stress analysis. Capabilities of stress solver. It performs 5 types of analyses: steady state, transient, resonant, harmonic, and buckling analysis. And it handles nonlinearity, geometrically nonlinear, large displacement and large strain. Nonlinear materials, that is elastoplastic creep, viscoelastic, and hyperelastic. It also handles the contact with friction. And it is capable of multi-step thermal load analysis. And birth and death are taken into account. Now let me explain the analysis types. As I said, you can perform 5 types of analyses. Static analysis, where you can simulate the deformation and internal stress caused by the static load. Transient analysis. Here, you are looking at the collision of the objects. You can solve the equation of motion over time steps. You can take the velocity and acceleration into account. Resonant analysis. Resonant frequencies and resonant modes are solved. Harmonic analysis. When you apply the vibration to the analysis model, it deforms due to the vibration, and you can simulate how the model deforms. Buckling analysis. You can simulate the buckling load and deformation caused by the compressive force. Now, let me show you 2 examples of the nonlinear analysis. First, compression. Here is a cross-section of an analysis model, the metal with a groove on the surface. We put an object in the groove. The object is made of rubber and apply the compression from the above. The rubber object is deformed, and you can see the compressive strain is generated within the rubber object. In this example, the nonlinearity, such as contact, hyperelastic material, and large deformation, are taken into account. The next example is the inelastic collision. The colliding balls show plastic deformation, and they are parting from each other. In this example, the transient analysis is performed, and nonlinearity, such as contact, elastoplastic material, and large deformation, are taken into account. Now, I would like to show you a multi-step thermal load analysis. You can take into account the temperature change over the time steps. This is a soldering process of IC chip on a circuit board. Circuit board, IC chip, and solder bumps. Step 1. Soldering temperature is 250 degrees and cool down to 25 degrees. Step 2, raise the temperature to 120 degrees. And step 3, apply the underfill and harden at 120 degrees and cool down to 25 degrees. In this analysis, you can take the temperature changes into account. Here, you can see the simulation results of internal stress distribution and the deformation on the right side. Results of the step 2. And from step 2 to step 3, we are seeing the birth of the underfill. And at step 4, the IC is activated and the temperature goes up to 85 degrees. Now, let's move on to the thermal analysis. Capabilities. It performs two types of analyses: the steady state and transient analysis. As a heat generation, you can set the temperature distribution, time dependency, and the temperature dependency. Heat radiation setting. You can set the natural convection, forced convection, and the radiation. Multiphysics is possible with stress analysis. The temperature distribution is handed over to the stress solver. Analysis type of thermal solver. There are two types of solvers: steady state and transient. In the steady state analysis, you can simulate the heat radiation and heat flux. In the transient analysis, you can analyze the body-to-body radiation, the time-dependent heat source. Now, let's take a look at an example of two analysis types: steady state and transient. Here is a heat source of 10 watts in the center of the square object. The four sides of the object are set to 0 degree. As the time passes, the temperature is going up. 80 seconds later, 160 seconds later, and 240 seconds later. Like this, the transient analysis simulates the temperature change over time. When reaching the steady state analysis can solve the final state of temperature. Now, I would like to touch upon the heat source and the natural convection. Now we are looking at the analysis model. This is a substrate, and we place two heat sources. One is 0.2 watts, and another one is 0.1 watts. And the heat is radiated in the natural convection. The simulation shows the highest temperature at the heat source of 0.2 watts. Now, the heat radiation. The analysis model consists of two plates and a disk in between. At the bottom of the lower plate, the temperature boundary condition of 1000 degrees is set. The arrows between the two plates indicate the body-to-body radiation. The analysis results show there is an area with a lower temperature due to the blocking by the disk between the two plates. Femtet has a tool to visualize the heat flows. It's called Thermal Cascade Viewer. Here is a simplified analysis model consisted of 6 bodies, for example. The heat source is 1000 degrees. The heat is flowing to the next bodies like this. and the heat is flowing to the ambient as well. Like this, you can visualize the heat flows by this tool. The operation is quite simple. Upload the results file to the tool. Then press the Visualize button. Then you can get the visualized heat flows. Now, the multi-physics of stress and heat. Here is an example of multi-physics of thermal and stress analysis. Again, I use the IC chip soldering process, for example. First, we perform the thermal analysis and get the temperature distribution. And then move on to the stress analysis from step 1, IC soldering. Step 2, raise the temperature to 120 degrees. Step 3, harden the underfill. And up to this, the uniform thermal load is applied. And here we take the temperature distribution into account and perform the coupled analysis. Now I will talk about fluid analysis and fluid thermal analysis. Fluid analysis solves the equations of motion, such as Navier-Stokes equation, continuity equation, and transport equation. Fluid thermal analysis takes into account the heat transfer by the flow. Now, what you can do with Fluid Solver? You can analyze the pressure loss, flow velocity, flow rate. And you can apply the results for your designing the flow path in the room, ventilation duct, heat sink, etc. Also, you can simulate the interaction of fluid and heat. If you are designing the electronics device, and if the device contains the heat source, how to manage the heat is a critical factor to design your devices. You can apply the results to your designing of heat management of electronics device, casing form, openings of casing and locations, form of heat sink and its effect, forced cooling by fan. Functionalities. Analysis types of the fluid solver are steady state, transient, and multiphysics of fluid and heat. Flow types to simulate are non-compressive flow, single-phase flow, forced convection, natural convection, laminar flow, and turbulent flow. Now, analysis setup. Boundary condition. You can set solid wall, slip wall, forced inflow and outflow, natural inflow and outflow. For multiphysics of fluid and heat, you can set to the solid the temperature, heat flux, dissipation to ambient, radiation and thermal resistance. And to the fluid body, you can set the heat flux on the wall, temperature of the wall, the inflow temperature. Here is an example of steady-state analysis. The analysis model has 5 openings, and in the center is a flow path. Forced inflow is set here, and the flow velocity is specified. Forced outflow is set here. The pressure is specified. Now we are looking at the results. At the 3 openings, the flows are mostly going out. This is an example of transient analysis. And this is a top view of the analysis model. I put a circular cylinder here. And the inlet and outlet are set. The air flows around the cylinder. The results of the simulation, starting from 0 second to 10 seconds later, 18 seconds later, and 50 seconds later. The current vortex is shed from the alternating sides of the cylinder. The transient analysis can deal with the changes of the flow over time. Now, the multiphysics, fluid thermocoupled analysis. Bidirectional analysis of interaction between fluid and heat is possible. It allows you to calculate the heat transfer by flow, acceleration of heat transfer by turbulent flow, temperature dependency of viscosity, and buoyancy by distributed temperature. Now, the example of the coupled analysis of fluid and heat conductance. First, we perform the steady-state analysis of fluid, and then move on to the steady-state analysis of heat conductance. The analysis model has a substrate. A heat source is placed on the substrate. The surrounding is the air. The inlet is set where the air of 25 degrees is flowing in at the velocity of 1 meter per second. The outlet for the natural outflow. Now the analysis results. The temperature distribution shows that the temperature tends to be higher on the downstream side of the airflow. This is because the airflow transports the heat to the downstream. Like this, the fluid thermocoupled analysis calculates the airflow and its effect on the heat transfer. Here is a multiphysics example of steady-state analysis of fluid and transient analysis of heat conductance. The analysis model is same as the previous one. The state of flow is steady. The temperature change is calculated every 60 seconds for 20 minutes. You can see the temperature is rising, and its distribution is changing over time. And the temperature reaches the steady state after 20 minutes. The third example using the same analysis model. In this example, steady state analysis is applied to calculate the heat dissipation by the natural convection. Natural convection is the airflow generated by the temperature difference. The surrounding air has boundary condition of natural inflow and natural outflow on every side. Temperature distribution. This is a cross-section of the model. The area above the IC chip shows higher temperature. It means the heat is transferred upwards. And here is flow velocity vectors of the cross-section of the model. We can observe the air is flowing in from the bottom of the air domain. Layer mesh. Layer mesh is for fluid body near boundary, where flow velocity changes rapidly and accurate simulation is needed. Here is a solid body of thin plate. The airflow is from the inlet to the outlet, and the slip walls are set. And meshing. Near the solid body and slip walls, the layer meshes are created automatically. That will give more accurate simulation. The flow velocity vectors near the wall surface. Horizontal axis is a flow direction. Vertical axis is a height direction from the wall surface. Near the solid wall, the flow velocity change is greater in the height direction than in the flow direction. By applying the layer meshes in the height direction, you can achieve more accurate analysis. Now I'd like to touch upon the piezoelectricity and sound. Piezoelectric analysis. It solves the pressure and the resulting voltage on the piezoelectric material. You can solve the Coriolis force and potential. And you can simulate the displacement and generated voltage. Coming to the acoustic analysis, you can solve the interference of sound waves, reflection and diffraction, radiation impedance, and directivity, acoustic impedance. And here is an analysis model of musical instrument. And you can see how the sound waves behave. Femtet is used in a wide range of applications, from automotive, electronics, precision instrument, materials, construction, machinery, energy, and educational institutions. One of the important factors when you select the simulation software is cost performance. We offer Femtet at the annual price of less than $2,000 for a package of 8 solvers and pre- and post-processors. And we have a variety of options of advanced magnetic, advanced mechanical, advanced thermal fluid, CAD data translator, and accelerator. Now, some of you may wonder how it is possible for us to offer the simulation software at such a low price. Here is a secret behind. To explain the secret, let me touch upon our company briefly. Murata is an electronic component manufacturer making various kinds of devices and components. And back in 1982, we developed Femtet for internal use. Since then, Femtet has been supporting Murata's R&D, engineering, and designing activities. And in 2008, we decided to introduce this tool to the world. By the time of commercial release, the development cost had been depreciated. So the price is very low, but the performance is not cheap. Thank you very much for watching. We are here to answer your questions by chat or text, depending on the time zones you are in. Thank you very much.